In this video, we introduce VRoot, a virtual reality application for manual root architecture reconstruction. Before I show footage, let us have a brief look at what this project is about. Plant roots are quite obviously more difficult to observe than the shoot part of the plant, but roots are just as important for the function of the plant. This has been extensively studied, and our main point of observation is 3D images from plant and soil columns. These are non-magnetic tubes in which, for example, sieved soil is filled and a plant is grown for a time. We scan these soil columns using different techniques, most notably an MRI scanner. The potential image quality is very high, but there's always a trade-off between easily separable roots and a realistic experimental setting. There is always, however, the question about noise within the data, and there has been a lot of previous work in that area. The first technique, which has been developed by Zhao et al., is the 3D unit segmentation of the soil column. The segmentation algorithm furthermore has the step of upscaling the data such that there is a larger voxel resolution while retaining the foreground-background separation of the image. This cleaner version of the data can be used by optimizers to find the tracing in the root system, but for these tracings to work, the globally optimal solution must also be the correct root architecture, which is not always the case. To mitigate this and to further increase extraction precision, we use virtual reality root tracing. The approach of VR manual reconstruction has been applied since 2013, where it was used for in situ root analysis. When we developed VRoot, we had very practical intentions of supporting researchers in their workflows. We wanted to produce a software on modern hardware with more intuitive interactions. Since then, our program has already been used to analyze the impact of the segmentation step on manual and automatic root reconstruction methods. Our workflow takes an MRI scan and optionally an existing tracing, and provides the user with the ability to adapt and trace roots manually with high precision. On a technical level, we have a data analysis and visualization server running in the background. This server is connected to the Unreal Engine, and they always share the root data that is rendered in VRoot. This data can be used to calibrate functional structural plant models as well as be used as boundary for functional simulations. VRoot consists of a menu and the interaction metaphors that make up the more fine-grained interaction. We show this example using the same device that was used for the study, an HTC Vive Pro. For data exploration, users can alter the signal cutoff, meaning the value of the ISO surface, to adapt the view on the data. This is mostly not necessary when dealing with segmented data, but can be very helpful when trying to extract root system architectures from particularly noisy data. Navigation within the virtual environment is mostly extrinsic, meaning that the root system and MRI scan can be moved within the space while the user navigates around it. Tracing and editing the root system architecture is done through editable nodes that the users can attach new segments to, as well as move the data. All interaction in VRoot is selection set based. If two segments are selected, the user can create new segments between them. Now, with only one segment selected, the user can draw by pointing to the end of the new desired segment. The selection will jump to the newly created segment, and the root topology is implicitly defined by the attachment. If something goes wrong, there are additional functionalities, such as undo, which restores the version before the last action was taken. If the data is particularly noisy, this is where virtual reality tracing really shines, as it is easier to navigate in 3D space if users have access to a 3D visualization of the scene. In our study, this was shown by a stark increase in the F1 score in the water noise condition. For dense annotations, as well as to adapt the whole organ at once, the editing widgets on the side always manipulate the current selection. They typically float next to the most recent addition to the selection set. This is a good way of fine-tuning the position and diameter of the segments. A good way of tracing a root system is by tracing the taproot very finely, by placing a lot of nodes into it. This not only helps with attaching laterals without needing to add nodes in between, but also makes the navigation through the root system a bit easier. New nodes will always carry over the diameter of the attachment parent, so it is good to set the correct diameter quite early. There is a lot of previous work on the question on whether to support sitting or standing, but for our purposes we chose to give the users the option to do either, especially relating to how they interact with the root system. Allowing users to adapt their posture according to their preferences is an important tool in increasing the accessibility of such a system. For the purposes of the user study and to retain uniformity across study tasks, we ask users to sit for the duration of the user study. This is also where the functionality of jumping the selected segment up or down the system comes in handy. Thank you for watching this video. The software will be available on GitHub, and we are working on a Meta Quest version.